Hi everyone. So this video is about the synopsis of hydrogen and it is entirely based on NCERT syllabus, and I have highlighted the important points to be remembered and what MCQs can come from this particular chapter that I'm going to discuss. So let's start. So first we are going to discuss about position of hydrogen in the periodic table. We know that hydrogen is the first element in the periodic table. However, its placement in the periodic table is debatable. If you recollect, hydrogen with the electronic configuration 1s1 should be placed in the group 1, but it is not placed in group 1, it is actually placed in the middle of the periodic table. Also, there is a resemblance of hydrogen with the halogens, which is group 17 of the periodic table. So let's discuss about this in detail. Hydrogen has electronic configuration 1s1. On one hand, its electronic configuration is similar to outer electronic configuration ns1 of alkali metals, which belongs to the first group, and on the other hand, like halogens with ns2np5 configuration, which belongs to 17th group of the periodic table, it is short by 1 electron to the corresponding noble gas configuration of helium, that is 1s2. Hydrogen therefore has resemblance to alkali metals, which lose 1 electron to form H plus proton, as well as with halogens, which gain 1 electron to form hydride ion. So with 1 electron in the valence shell, if it loses, it can form H plus, and if it gains, it can form H minus. So it has resemblance to alkali metals as well as halogens. H plus, that is proton, approximately the ion size is 1.5 to 3 picometer. This is extremely small as compared to normal atomic and ionic sizes, which range about 50 to 200 picometer. As a consequence, H plus does not exist freely and is always associated with other atoms or molecules. Like alkali metals, hydrogen forms oxides, that is H2O, halides HX, sulfides H2S. However, unlike alkali metals, it has a very high ionization energy and does not possess metallic characteristics under normal conditions. We know that all alkali metals have metallic character and low ionization enthalpy. Hydrogen differs in that respect. In fact, in terms of ionization enthalpy, hydrogen resembles more with halogens. If you look at the values, delta H ion, that is ionization enthalpy, thermodynamic parameter, of lithium is 520 kilojoules per mole, fluorine is 1680, while that of hydrogen is 1312 kilojoules per mole. So, if we compare the lithium, fluorine and hydrogen ionization enthalpy, the ionization enthalpy of hydrogen has resemblance to halogens and not with the alkali metals, which have a low ionization enthalpy. Now, similarity to halogens. Like halogens, it forms a diatomic molecule, that is H2, combines with elements to form hydrides, like metallic hydrides, and a large number of covalent compounds. However, in terms of reactivity, it is very low as compared to halogens. Now, the reactivity basically is dependent on bond dissociation enthalpy, and the bond dissociation enthalpy of hydrogen is very high. That's why its reactivity is very low. That we'll study in chemical properties. In spite of the fact that hydrogen to a certain extent resembles both with alkali metals and halogens, it also differs from them as well. Thus, it is unique in behavior and therefore best placed in the middle of the periodic table. So now let's talk about dihydrogen, that is H2. Occurrence. Dihydrogen is the most abundant element in the universe, 70% of the total mass of the universe, and is the principal element in the solar atmosphere. However, due to its light nature, it is much less abundant, that is just about 0.15% by mass in the Earth's atmosphere. In the combined form, it constitutes 15.4% of the Earth's crust and the oceans. In the combined form, besides in water, it occurs in plant and animal tissues, carbohydrates, proteins, hydrides, including hydrocarbons, and many other compounds. When we talk about hydrides, then we are just not talking about H negative ions, we are talking about all hydrogen containing compounds. The compounds formed by the reaction of both metals and nonmetals are referred as hydrides for convenience. Now, isotopes of hydrogen. Hydrogen has famously three isotopes: protium, deuterium, and tritium. The predominant form is protium with a very high abundance. The tritium concentration is about 1 atom per 10 raised to 18 atoms of protium, meaning it is very less abundant, and of these isotopes only tritium is radioactive and emits low energy beta particles. Preparations of dihydrogen, that is H2. There are a number of methods for preparing dihydrogen from metals and metal hydrides. Let's first talk about laboratory preparation of dihydrogen. It is usually prepared by the reaction of granulated or powdered zinc with dilute hydrochloric acid. The reaction is Zn plus 2HCl gives ZnCl2 with the liberation of H2 gas. It can also be prepared by a reaction of zinc with aqueous alkali, and zinc with NaOH in the ratio 1:2 gives Na2ZnO2 and liberates H2. And this compound of zinc is named as sodium zincate. Na2ZnO2 is called sodium zincate. From this two reaction, we can also conclude that zinc has a tendency to react with acid as well as base, hence it is amphoteric. Zinc is amphoteric, and on reaction with acid or base, it liberates the hydrogen gas. Commercial production of dihydrogen. The commonly used processes are outlined below. First, electrolysis of acidified water using platinum electrodes give hydrogen gas. We know that electrolysis of pure water is not possible, but with the traces of acid or base, it can break down into H plus and OH minus. The H plus ions will move towards the cathode and will undergo reduction to form H2 gas, and the OH minus ions would move towards anode and would undergo oxidation to form oxygen gas. So, 2 moles of water produces 2 moles of hydrogen and 1 mole of oxygen, meaning electrolysis of water produces hydrogen and oxygen in the ratio 2:1. High purity, about 99.95% dihydrogen, is obtained by electrolyzing warm aqueous barium hydroxide solution between nickel electrodes. It's a factual point to be remembered. High purity, about 99.95% pure dihydrogen, is obtained by electrolyzing warm aqueous barium hydroxide, and the aqueous solution of BaOH twice is also called baryta water. BaRYTA, baryta water. So on electrolysis between nickel electrodes, it can produce dihydrogen on a large scale and a very pure and with high purity. It is obtained as a byproduct in the manufacture of sodium hydroxide and chlorine by the electrolysis of brine solution. So during electrolysis, brine solution is 10% of NaCl, and in the solution we will have H plus, Na plus, Cl minus and OH minus. So as per the preference for redox, the Cl minus move towards the anode, undergo oxidation and liberates a greenish yellow gas, that is Cl2. And at cathode, H plus ions would gain electron to form H2 gas. So the overall reaction is NaCl aqueous liberates chlorine gas at the anode, hydrogen gas at the cathode, and produces sodium hydroxide. Next, reaction of steam on hydrocarbons or coke at high temperature in the presence of catalyst yield hydrogen. Steam on hydrocarbons or coke, like methane plus H2O, or for that matter any other hydrocarbon with water at a high temperature of 1270 Kelvin in the presence of nickel as catalyst, carbon oxidizes to carbon monoxide and water reduces to H2 gas. Carbon oxidizes to carbon monoxide and water reduces to hydrogen gas. Now, the mixture of carbon monoxide and hydrogen is called water gas. As this mixture of CO and H2 is used for the synthesis of methanol and a number of hydrocarbons, it is also called synthesis gas or very famously called syn gas. The reaction of CO and H2 in the ratio 1:2 in the presence of copper, zinc oxide, alumina at a high temperature produces methanol, and that is an important preparation for CH3OH or methanol. Likewise, CO and H2 can be used to prepare large number of hydrocarbons. That is why it is famously called synthesis gas or syngas. Nowadays, syngas is produced from sewage, sawdust, scrapboard, newspapers, because from that we can obtain methane, which can be further added with steam to produce the water gas. The process of producing syngas from coal is called coal gasification. So coal or coke, when added with steam, again at 1270 Kelvin, carbon oxidizes to CO and water reduces to H2 gas. The production of dihydrogen can be increased by reacting carbon monoxide of syngas mixtures with steam in the presence of iron chromate as catalyst. So this carbon monoxide is added with steam at 673 Kelvin in the presence of FeCrO4, iron chromate FeCrO4, carbon monoxide changes to CO2 and from water we get H2. This is called water gas shift reaction. Water gas shift reaction, and the process is also named as Bosch process. So we can call it as coal gasification or water gas shift reaction or Bosch process. A very important and a simple reaction. Carbon dioxide is removed by scrubbing with sodium arsenide solution. So this CO2 could be removed by scrubbing with sodium arsenide solution, or we can absorb in alkali. Carbon dioxide is an acidic oxide, so it can be absorbed in alkali, that is KOH. Presently about 77% of the industrial dihydrogen is produced from petrochemicals, 18% from coal, 4% from electrolysis of aqueous solution, and 1% from other sources. Properties of dihydrogen. Physical properties. Dihydrogen is a colorless, odorless, tasteless, combustible gas, and it is lighter than air, insoluble in water. Next, chemical properties of dihydrogen. The chemical behavior of dihydrogen is determined to a large extent by bond dissociation enthalpy. That's the amount of energy required to break the HH bond. The HH bond dissociation enthalpy is the highest for a single bond between two atoms of any element, meaning H2 molecule is highly stable, and to break the HH bond, the amount of energy required is enormously high. It is relatively inert at room temperature due to this high HH bond enthalpy. Thus, The atomic hydrogen is produced at a high temperature in an electric arc or under ultraviolet radiation. A very important point. The atomic hydrogen is produced at a high temperature because the energy required to break the HH bond is very high, and this high temperature is produced in an electric arc or under ultraviolet radiation. Since its orbital is incomplete with 1s1 electronic configuration, it does not combine with almost all the elements. It accomplishes reactions by loss of the electron to give H+, gain of an electron to form H-, or sharing electrons to form a single covalent bond. So basically, it follows the kind of octet rule where the bond could be formed by losing, gaining, or sharing electrons to complete the duplet and achieve the nearest stable inert gas configuration of helium, that is 1s2. So the chemistry of dihydrogen can be illustrated by the following reactions. The reactions are highlighted. Reaction with halogens. It reacts with halogen X2 to form hydrogen halides, where halogen could be fluoro, chloro, bromo, or iodo. While the reaction with fluorine occurs even in the dark, with iodine it requires a catalyst. The reason is, among the halogens, fluorine is most reactive, and down the group the reactivity decreases. So the reaction with fluorine would be vigorous and could also occur in the dark, but with iodine the reaction would be slow, and that's why it will require a catalyst. Reaction with dioxygen. It reacts with dioxygen to form water, and the reaction is highly exothermic because it's a combustion reaction where hydrogen burns in oxygen in the presence of catalyst to form H2O, and the enthalpy of formation of water per mole is minus 285.9 kilojoules. Reaction with dinitrogen. With dinitrogen it forms ammonia by a well-known process called Haber's. And here the H2 and N2 reacts in the ratio 3:1 at 673 Kelvin under 200 atmosphere pressure in the presence of iron as catalyst with molybdenum as promoter to give 2 moles of ammonia. And even this reaction is an exothermic reaction where for per mole of ammonia the energy liberated is 92.6 kilojoules. Reaction with metals. With many metals, it combines at a high temperature to yield the corresponding hydrides. So, H2 reacts with the metals to form metal hydride, where M is an alkali metal. So, H2 reacts with 2 atoms of sodium to form 2 NeH, that is sodium hydride. Reaction with metal ions and metal oxides. It reduces some metal ions in aqueous solution and oxides of metals less active than iron into corresponding metals. Remember, it reduces some metal ions in aqueous solution and oxides of metals which are less active than iron into corresponding metals. So H2 reacts with palladium 2 plus ion. H2 itself oxidizes to 2H plus and palladium 2 plus reduces to Pd. So here H2 undergoes oxidation and behaves as a reducing agent. H2 is a good reducing agent, and that's the reason it could convert the oxides of metal into the corresponding metal. And this is a metallurgical reaction. And a point to be noted that this reduction could be done only for the metals which are less active than iron. For example, the active metals like sodium, magnesium, aluminium, their oxides could not be reduced by hydrogen because it is not so strong as a reducing agent. That's why it can convert the oxides of metal which are less active than iron to corresponding metal and the formation of water. Reaction with organic compounds, a very important reaction. It reacts with many organic compounds in the presence of catalysts to give useful hydrogenated products of commercial importance. For example, hydrogenation of vegetable oils, which are unsaturated hydrocarbons, using nickel as catalyst gives edible fats, which are saturated hydrocarbons. And margarine and vanaspati ghee belongs to the family of edible fats. So vegetable oils, unsaturated hydrocarbons, can be hydrogenated with nickel as catalyst to give saturated hydrocarbons, that is fats. Hydroformylation. If you look at the word, hydroformylation is similar to hydrohalogenation, where hydrohalogenation means addition of hydrogen and halogen. So hydroformylation would mean addition of hydrogen and formyl group. Now, formyl group is the other name of aldehyde group, that is CHO. So here the H and the CHO is going to get added across the double bond. So that is hydroformylation of alkenes, which are also called olefins. Hydroformylation of olefins yields aldehydes which further undergo reduction to give alcohols. This is also an important reaction for water gas or syngas or synthesis gas, and this is one of the application of the syngas to produce the organic compounds. So H2 plus CO gets added to an alkene, R2CH double bond CH2. Now here H2CO could be considered as formaldehyde HCHO that could break down as H and CHO group. Now that gets added across the double bond. So here the H gets added to carbon having less H and CHO gets added to carbon having more H. So the product would be a straight chain aldehyde, that is RCH2 CH2 CHO. This aldehyde further undergoes reduction with H2 to form an alcohol. So the H2 gets added across the C double bond O group. The CHO could be considered as CH double bond O. So one H will be added to carbon and one H to oxygen, giving you R CH2 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 OH, which is a straight chain primary alcohol. So hydroformylation of alkenes yields aldehydes which further undergo reduction to give the straight chain alcohols. Now let's look at uses of dihydrogen. The largest single use of dihydrogen is in synthesis of ammonia via Haber's process, which is used in manufacture of nitric acid through Ostwald's process and nitrogenous fertilizers like ammonium phosphate or ammonium sulfates. Dihydrogen is used in the manufacture of vanaspati fat by the hydrogenation of polyunsaturated vegetable oils like soya bean, cottonseeds, etc. The reaction we have already seen. It is used in manufacture of bulk organic chemicals, particularly methanol. Now this is the important reaction of syngas to produce methanol on a large scale. So CO plus 2H2 in the presence of cobalt catalyst or copper zinc oxide Fe2O3 catalyst forms methanol, that is CH3OH. It is widely used for the manufacture of metal hydrides. Used for the preparation of hydrogen chloride, a highly useful laboratory chemical. In metallurgical process, it's used to reduce heavy metal oxides to metals, and this is the reaction we have already studied. Atomic hydrogen and oxyhydrogen torches find use for cutting and welding purposes. We have already seen in chemical properties that the HH bond enthalpy is enormously high. Now here, atomic hydrogen is formed by passing dihydrogen gas through electric arc stuck between two tungsten electrodes when dihydrogen molecules dissociates into H atoms. The life period of atomic hydrogen is just 0.3 seconds. Consequently, it returns to molecular hydrogen readily, liberating a large amount of energy which in turn is used for welding purposes. And this is the basic principle of atomic hydrogen arc welding or atomic hydrogen torch. So atomic hydrogen atoms, which are produced by dissociation of dihydrogen with the help of an electric arc between tungsten electrodes, are allowed to recombine on the surface to be welded to generate the temperature of about 4000 Kelvin. Dihydrogen is used as a rocket fuel in space research. It is also used in fuel cells for generating electrical energy. The first fuel cell used in the form of hydrogen was hydrogen-oxygen fuel cell. It has many advantages over conventional fossil fuels and electric power. It is efficient, it is pollution free, so it does not produce any pollution and releases greater energy per unit mass of fuel in comparison to gasoline and other fuels. We'll learn about this efficiency of dihydrogen as fuel in the later part of the synopsis.